Alright, I would like to talk a little bit about another concept that is still related to resonance and still related to damping, which is the concept of base excitation. This is also very important when we talk about vibration dissipation. So when we have bodies that are subjected to external vibrations, very often we don't want actually those external vibrations. There are very few cases in which we want the vibrations, which is, for example, when we want to build or design or build like an energy harvester, for example, based on vibration. But in general, we don't want. We want to actually suppress them. And we can talk a little bit about base excitation to have a little bit better understanding. So we can start from a schematic of a certain mass that is connected to a certain spring and a dashpot, and then we can assume, this can be actually a very simple schematic for a car suspension, for example. So where we have the mass of the car, and then we have a certain dashpot, we have a certain spring, and then we have also the wheel. In this case, we are assuming that the wheel is massless in comparison with the mass of the car. And then we can pretend that this car is actually driving along a certain road, and then we can, what we want to do, we can actually consider this like as another body, like the base of the wheel, basically. So in this case, what we should do, we should look at what's going on in terms of displacement to both bodies. We can see what's going on to the mass, and we can see what's going on to the base. So which means that in this case, the motion of the two masses, like the mass and the base, is independent. Since these two move independently to each other, because we can have an extension of the spring and the dashpot, or we can have a contraction of the two, which means that the relative position and the relative velocity can change. This is not a rigid body anymore, but we are actually looking at two bodies. This is a little bit of introduction, a little bit of, say, transition between single degree of freedom and multiple degree of freedom. So let's think a few minutes about this situation. So if this is the case, that we have like an independent motion for the mass and the base, one parameter is not enough anymore, but we have to use two parameters to describe what's going on in this body, which means that we can use let's say the coordinate x to describe the motion of the mass, and we can use the coordinate y to describe the motion of the base. Right. So I want you to think a couple of minutes on how we can determine, how we can write, for example, the equation of motion for a situation like this. Right, any idea on what we should do to find the equation of motion of this mass subjected to a certain base excitation? We can treat the rod as a forcing function, I agree. So which means that we have to draw like a free body diagram of the mass, and the forces that act on the mass are for sure the gravity, And also the other two forces that act on the mass are the force from the spring and the force from the dashpot, right? How can we model these two forces according to the parameters that we have here in the system? So how much is the force that the spring exerts on the mass, and how much is the force that the dashpot exerts on the mass? They will be also a function of y. Yes, they are. They are both actually, they are function of both x and y. Because what we have here, what's going on like between the mass and the base, is basically that it can happen that the mass and the base get closer to each other, or the mass and the base can get away from each other. Which means that if we look at the spring, if they get away from each other or get close to each other, basically the force of the spring here, Fk, can be modeled as the elastic constant of the spring, K, multiplied by what? By the difference between the displacement that comes in x and the displacement that comes in y. Think about this. If the two move exactly in the same, by the same amount, the spring is not contracted or stretched, which means that it doesn't exert any force on the mass. So the force from the spring to the mass comes only we have some difference in the displacement from x and the displacement from y. Makes sense? So we can again model this force as k times x minus y, and similarly we know that the force from the dashpot, we can call this Fc, depends on the relative velocity between the mass, between the mass and the base. So if this is the case, we can write as c, and then the difference between x dot and y dot. Again, if the mass and the base move at the same velocity in the vertical direction, it means that from the dashpot there is no force. So how do we model this one? We look at the difference between the velocity of the mass and the velocity of the base. Makes sense? So we can now assume that the force, the external forcing force, which is actually the motion of the base. Again, we said that we could treat this as an external force, but it's more an external displacement actually. So we can again model this, and we can assume that it has this form. I used okay, we can model this y of t as a capital Y, or like big Y, multiplied by sine of, we call omega bt, because we will distinguish as well. So of course what we need is y, and we need also y dot, because we will need to plug this here. So if y of t is y sine of omega bt, y dot will be equal to big Y and then omega b cosine of omega b t. I think this time I put all the needed omegas. So from here we can look at the equation of motion. So we can basically split kind of the contribution of the x, the contribution of y, because if we write the equation of motion, summation of forces equal to mass time acceleration, we will have something like this. We will have m x double dot plus kx plus c x dot. Again, on one side we put the contribution of x. This will be equal to k and then big Y sine of omega bt, and then plus c, and then also big Y omega b cosine, sorry I don't have a lot of space, I will write here omega bt. So this term here will be the term k times y, and this term here will be the term c times y dot. Now I don't want to go too much in the details, just a couple more steps to see how mathematically this should be solved. So when we also normalize in this case, which means we divide by the mass of the body, because here the term, the coefficient of x double dot is simply the mass, we can also rewrite again using the damping coefficient and the natural frequency. So in that case the equation becomes like this: x double dot plus 2 zeta omega n x dot plus omega n square x equal to omega n square and then big Y sine of omega b t, and then we have the last term plus 2 zeta omega n omega b and then big Y, and in this case we have the cosine of same thing omega b t. So in the previous cases we had the three terms on the left hand side of the equation equal to one term of on the right hand side. In this case we have two terms, which means that actually we can split the particular solution as summation of two particular solutions. Again, mathematically of course this becomes a little bit more involved, so again I don't want to spend too much time on this, but basically what we obtain eventually in terms of solution is something that looks like this. And of course in the textbook you can find more steps that I'm showing now, but again I want to focus on the final result. So we have that the final solution would look like this. I can give this step. Will be the particular solution. Omega t and then y omega n squared plus 2 zeta omega b squared, and then in the denominator we have omega n squared minus omega b squared, and then plus 2 zeta omega n omega b. This is also squared, and this term multiplies the cosine of omega bt minus theta 1 minus theta 2. Now the important part that we should look at, even in this case we can introduce the transmissibility, we can introduce the frequency ratio as we did before as lowercase r, which is the ratio between omega and omega n. When we introduce this we can finally rewrite in the final form the equation as the solution like this. We have 1 plus 2 zeta r squared divided by 1 minus r squared plus 2 zeta r squared, and then everything is square root. So the very last step actually is to divide this amplitude by this big Y. I'm not going to write all this, I will simply cancel from here and I will put here on the bottom, because this term here, the ratio between the amplitude of the displacement of the mass and the amplitude of the displacement of the base, is called displacement transmissibility or transmissibility ratio. So basically this quantity here is telling us how much displacement we have on the mass with respect to the amount of displacement that we have from the base. This big X over big Y. And exactly like we did with the damped force system, we can plot this quantity with respect to our parameter R, which is also the frequency ratio. Now when we plug this function with respect to R from the textbook, this is what we obtain. This is on page 154 of the textbook, and now we can see something that is a little bit more, more detailed than what we saw before when we were looking at the amplitude of damped force system, because similarly to what we had before, we can see that when R, this is a frequency ratio, is equal to 1, we still have an increase of the amplitude. And of course, depending on what value of zeta we have, if we have a bigger value of zeta, it means that we are kind of we are reducing the amplitude of vibration, so we have a lower peak. But there is another, so the value of 1 for the frequency ratio is still very, very important to look at. But then there is another very important value, which is this value here, this square root of 2. Because if you look at the graph, what happens when the frequency ratio is smaller or greater than square root of 2, there is basically a switch in the behavior. Because if R is lower than square root of 2, an increase of the damping ratio determines a decrease of the amplitude. On the other side, when R is greater than square root of 2, an increase of the damping ratio determines actually an increase of the displacement, an increase of the amplitude of vibration. Makes sense? So when we design our vibrating systems, or when we design our systems and we know that they will be subjected to a certain vibration, to a certain external dynamic force, we need to always make sure that we look at these two values so that we don't have an increase of the amplitude of vibration that is not desired. So in general, we can say that when the value of R is lower than square root of 2, basically the system amplifies the input from, in this case it was the rod. Because if you look at the value of the displacement ratio, when r is lower than square root of 2 is always greater than 1. It starts from 1, but then it suddenly goes up. So it means again, when r is smaller than this number here, square root of 2, again we have an amplifier basically. Our system behaves as an amplifier. So if we have a certain input, a certain amplitude of the input, the amplitude of the output will be bigger for sure. On the other hand, if the value of r is greater than square root of 2, we always have that the displacement ratio is smaller than 1, is below this value of 1, which means that we can use this to reduce the vibrations that come from an external source, from a base excitation. This is how we have been calling them. Makes sense? So if you want to reduce vibrations, we need to have r greater than square root of 2. When we talk about base excitation. Makes sense? Any question about this? Alright, if there are no questions, we are done for today and we are going to meet again Wednesday. Alright? Alright, thank you very much and have a good night.